Hi, everybody. Welcome, everybody, to the GCAN webinar series event. My name is Jennifer Vreeland Dawson, Research Associate for GCUS, and I'll be hosting today's presentation. For those joining us today who are not familiar with GCAN, GCAN is the Gulf of Mexico Coastal Acidification Network, a regional group developed through a partnership between NOAA's Ocean Acidification Network and the Gulf of Mexico Coastal Ocean Observing System. During our webinar events, we ask that everyone hit the mute button and that all questions wait until after the presentation. However, feel free to type in a question in the chat box throughout, and I will read them after the talk. This is our second webinar to kick off 2018, and with that, we have the pleasure of featuring the University of Mississippi's Dr. Stephan Howden and his work, Autonomous Monitoring of Ocean Acidification Parameters in the Hypoxic Zones of the Northern Gulf of Mexico. And with that, I'd like to introduce and hand the discussion over to Dr. Howden. Hello, Dr. Howden.
Hi, Jennifer, thank you. And thanks for Kelly for helping us out with this. All right, I'm just getting the presentation ready. Okay, so is it?
There we go.
All right. Whoops. Every time I hit that control thing, it
You're quick with the clicker.
comes out of the presentation mode. All right, I won't move it. It just obscures some of my view of the slide, but all right, well, thank you very much. Today I'm going to talk about some observations in the Northern Gulf of ocean acidification parameters, and that mostly involves the pH and CO2, because those are the two sets of instruments that we have for the autonomous monitoring. There are a lot of people who have contributed to various products that I'm going to show you, the various data products. And I'm not a biologist or marine chemist, so if I make any mistakes, those are my mistakes. Those are not mistakes of any of these people. So my outline is I'm going to give an introduction to the study area. So I'm going to point out some features in the Northern Gulf, describe what the Western Mississippi Bight is, for those who aren't familiar with it. And most people are familiar with hypoxia in the Louisiana-Texas shelf. So I'm going to give some information on hypoxia east of the Delta in the Western Mississippi Bight. And after that, I'm going to get into the observations and analyses to date of data from the USM Central Gulf of Mexico Ocean Observing System buoy, which, if you go to the NOAA PMEL website, is identified as Coastal MS, or Coastal Mississippi. And that operated in that location with the MAP CO2 system from 2009 to 2017. And then I'm going to show results from a wave glider in 2012 and 2013. We had 2 deployments that went around from the buoy location in the Mississippi Bight around the Delta and back, and that had a PCO2 system from Mbari. And then I will, so the buoy has subsequently, since July of 2017, been moved over to the so-called dead zone off of Louisiana. And so I'm going to show results from that record, and then touch on some discussion points. So up in the top left, you can see a map of the central Northern Gulf, and that area between the Mississippi Delta, Mississippi River Delta, and southeast Louisiana, and Cape San Blas, which is that kind of protrusion coming south and on the Florida Panhandle, is called the Mississippi Bight. And in the bigger picture, you can see what I've indicated as the Western Mississippi Bight, which has some distinct circulation and biogeochemical um, signatures compared to the eastern side, and primarily that's because you have Mobile Bay outflow and then a lot of smaller rivers, and then there's some influence of the Mississippi River. Um, and then for later, I wanted to point out that there is a spillway that goes from the Mississippi River into Lake Pontchartrain, and there's a little yellow arrow where that spillway is labeled BCS, which stands for Bonnet Carré Spillway. And so when the river in New Orleans reaches 1.25 million cubic feet per second, which is about 35,000 cubic meters per second, that spillway is opened, dumping water into Lake Pontchartrain. And then it flows out. I have a dashed arrow from Lake Pontchartrain over towards the Mississippi Sound through that's the largest pass, what's called the Wrigley's. And so the water will be diverted into Lake Pontchartrain and then over to the Western Mississippi Bight. And then down in near the lower, closer to the lower left of the figure, there is a icon showing where the Singuz buoy has been moved to in July of 2017, and it's very close to a LSU WAVESYS station, CSI 6. All right, so an interesting thing about this area is that even though there's a lot of fresh water into the Mississippi, the Western Mississippi Bight, the nutrient loading is low compared to the Mississippi Atchafalaya system. So these figures are from Turner and Rabelais 1999, where they divided the shelf of the Gulf of Mexico into these regions. Region 6 is the Mississippi Atchafalaya, and you can see in the bar graph that the nutrient loading, the nitrogen and phosphorus, is very large. And then when you get over into Region 7, which includes the Western Mississippi Bight, it's quite a bit lower. And, you know, an open question has been how much of the Mississippi River water actually makes it up into especially the northern part of the Western Mississippi Bight and affecting the biogeochemistry of the region. Now I'm involved in a consortium, a GOMRI funded consortium, and as part of that, we've been doing sampling in the Mississippi Bight. There were cruises in the fall of 15, spring of 16, and the summer of 16. And based on Dello 18 measurements, Alan Schiller found that Mississippi River water was very small quantities in the Western Mississippi Bight. So at least during those time periods, there didn't seem to be a large amount of impact. To give you an idea of the freshwater inputs, there's a satellite view of various plumes coming out of, there's the plume coming out of the main pass at Mobile Bay, several remnant plumes coming out of the passes to the barrier islands, and you can see also from the Mississippi Delta. And if you add up all that freshwater input directly into the northern part of the Western Mississippi Bight, it totals up to about 16% of the combined Mississippi Atchafalaya inflow. So it's a substantial amount of fresh water. Mobile Bay, I think, is the 5th largest freshwater discharge in North America. And then not all the Mississippi River water goes west. For example, Donnell and Weissman found that 53% of the Mississippi River water goes west and the remainder goes east and offshore, but they didn't really quantify how much might go to the northeast or not. All right, so now I want to shift the focus over to hypoxia in the Western Mississippi Bight. And this figure is from a paper by Brunner et al., 2006. And in the top figure shows the results of an index of hypoxia tolerant to intolerant forams in sediment cores. So the tops of sediment cores taken in the 1950s that she had access to. And there was a region in that you see the red region is an area where there was a predominant number of forams that are hypoxia tolerant. And at about the same time as she was working on that result, the two of us went out and did a little survey of hypoxia, and bottom water survey in August of 2006, and found a region of bottom water hypoxia that kind of matched up pretty nicely with what the sediment cores had shown. So partly to address that, a group of us at USM were funded through the Northern Gulf Institute to run a monitoring program. And the green dots here are stations that we occupied mostly on a monthly basis, but due to weather and travel things, sometimes we weren't able to get to each one every month. But we went from 2007 to 2011, and it ended at Station 8, which is on the 20-meter isobath. And that's where the Singus buoy mooring location is. We had been operating a mid-ocean buoy there since 2004. So we ran this sampling line out to that buoy. And here's a time series from one of those stations. So in the map above, I've circled the station. That was our station 6. And I've got a time series on the top and then 3 Hofmahler diagrams. The inverted black triangles show when the cruises were, so you can get an idea of where the data actually are. So it's kind of sparse, but you can see that there is, so the top panel is the available potential energy per unit volume. And you can see that it ramps up in the spring and has a maximum about July. So that's a measure of how much energy is needed to mix the water column. So from March until July, the water column is becoming very stratified and very stable. So the following 2 panels are salinity and temperature. And you can see around March, the salinity starts getting higher. There's indications of upwelling into June, July. There's a wind shift that occurs in the May-June timeframe where the winds become predominantly out of the southwest or the south. And that creates kind of an upwelling situation in this right angle area of the coast. And down at the lowest panel is the dissolved oxygen. And the white contour is the 2 milligram per liter contour. So you can see that this, we have salinity upwelling, and you have, there's hypoxia that ends up coming up in the water column with that high salinity. And then here's at the buoy location. There are fewer times we're able to get to the buoy, so the data is a bit more sparse. But again, you can see that buildup of the available potential energy peaking in July, upwelling of high salinity waters, and associated hypoxia at the seafloor and up into the water column. And so the stability of the water column is being driven by not only the upwelling of all this high salinity water coming in, but of course the fresh water plume that comes out peaking in March through early June, and the seasonal heating. To give you an idea of the development along the transect, I've plotted for 2011. Up above is salinity, and so it's a salinity along that transect going offshore, March through August, and you can see the freshwater plume starting to come out in March. And May, you really see a strong freshwater stratification, and then between May and June, you see salinity, higher salinity waters upwelling into the region. And then down below, you can see how the dissolved oxygen develops over the same time periods, and we get a slug of bottom hypoxic waters. And then in 2008 and 2011, we measured more and thicker hypoxia than we had measured the other years, and those years were not coincidentally years when the Bodden Carry spillway had been opened. But so we went out and did mapping cruises on small boats to map out the bottom dissolved oxygen. We weren't able to capture the full extent of the hypoxia because we were limited by our small boats and time we had available to do the sampling, but we measured very extensive regions of bottom hypoxic water in July 2008 and August 2011. So the left column is the dissolved oxygen in milligrams per liter, and the right column is the thickness in meters of the hypoxic layers. So you can see in 2008, we had hypoxic layers as much as 10 meters off the bottom of the water, which is a significant fraction of the water column there. And I'll note that in the summertime cruises for our Go Marie consortium, similar thicknesses were measured of hypoxia in this region. It turns out that in 2011, Nancy Rabelais was able to extend her hypoxia survey over to east of the Delta. And this is what, the map on top shows the region she found of hypoxic bottom waters. So it's very similar to what we saw. And again, she was not able to find the edges of the hypoxic zone there. All right, so so that doesn't have anything directly to do with ocean acidification, but of course there is this this phenomenon where you have bottom hypoxic waters. The geochemistry causes there to be low the pH to drop. So on the right, I show a schematic from Kai et al. 2011. And if you have the bottom waters capped off and there's respiration going on, then so you're losing oxygen, you're decreasing the pH, and we have some water samples for that program from 2008 to 2007 to 11. We didn't take water samples for carbonate system parameters, but we did do some of them for the ocean acidification work. And so here I've plotted at the buoy location where we had bottle samples at the bottom that we sent off to Wei-Jung Kai's lab for analysis. And you can see the low pHs at low dissolved oxygen levels and vice versa. Okay, so now onto the buoy. So here's a photograph, two photographs of the buoy. We have a 3-meter discus buoy, and we modified the hull to hold the MAP CO2 system that PMEL developed. And so there's 3 instrument wells, one for the gas standard, one for the battery, one for the electronics. And then there's a moon pool in the buoy with the equilibrator that goes down into the water, and it's got a float on it, so it sits in the moon pool, but the copper piping for it stays at the same water depth because the float allows it to ride up and down with any wave action that may come up into the moon pool. And then there's an air block for the atmospheric sampling that's up near where the solar panels are. So as I mentioned, on the PMEL website, this buoy is referred to as Coastal Mississippi. So I'll refer to it as a Sengoose buoy or Coastal Mississippi. And here's the time series from the buoy. So at the top we have in red is the XCO2 air, blue is water. Then the next one is pH, then salinity, temperature, dissolved oxygen, and then the wind speed corrected for 10 meters. And there are a couple of gaps. There are a few gaps in the time series for the MAP CO2 system. If anybody's interested, I can tell them what happened with each gap. The first one, we had a failure of the buoy system when after we had deployed it, and we didn't have another replacement buoy at that time because we were turning around the second buoy, so we had not another buoy to put in. But the pH, we didn't have a pH sensor until 2014, and we've had a lot of trouble keeping those working. So once PMEL provided us with a pH sensor, they've worked for a certain amounts of time, and then they cut out. In the temperature and salinity record, where there are gaps when the CTD failed, I've filled them with a climatology from the observations. So if you look at some of the how some of the variables covary, there is DO and pH at the buoy covary as you'd expect. One of the problems with measuring CO2 and pH and trying to constrain the carbonate system is that they covary, as you see in that top right plot. So that increases uncertainties in other parameters that you want to estimate from those two. Okay, so now if we look at the mole fraction of CO2 from the atmosphere, there's a time period which we haven't figured out what happened, but where the data are corrupted somehow. So we haven't figured out why that happened. But excluding that data from the analysis, visually you can see there's a seasonal cycle to it, as you'd expect. And if I fit a trend, so the black is the trend to the data with excluding that bad data, I get a trend of 2.54 parts per million per year, which is over that whole time period, which agrees fairly well with the globally averaged rates estimated by NOAA, seen in the table. If we look at the seawater record, again, there's some things that we haven't explained yet, like that big peak in 2014. If I exclude that peak and anything over 502 parts per million, then I actually get a negative trend of 1.45 parts per million per year. So it's kind of interesting that despite the increase in the atmospheric CO2, there's a decreasing trend in the seawater CO2 at this location. And if we look at the integral timescales, for salinity, it's 22 days at this location, but for the CO2, the mole fraction of CO2 in the seawater, it's only 13 days. If we zoom in on 3-week time periods, so you can see the variability, the high frequency variability better, you can see there's kind of quasi-diurnal oscillations to the CO2 levels. And one of the things that I want to get to in the future is doing wavelet analysis, because the statistics of this are not stationary. So the variance changes with time, depending on what chunks of time you consider. So as you'll see for the monthly climatology, for example. So I've looked at the spectra of it, but I want to look at a wavelet analysis, which can take into account how, for example, the diurnal variability can change. So here's the monthly mean climatology of the mole fraction of CO2 from the atmosphere, from the atmospheric measurements and the oceanic measurements. So the left column is the monthly mean, and the right column is the standard deviation of that monthly mean. So you can see in the atmospheric record, there's a very, sinusoidal looking variation. Peaks in February, between December and February. And then there's a low in the July through September time period, with the higher standard deviations occurring in August and September, and also December. So I need to do some more analysis to see if that's related to that high variance on those in August and September is due to tropical storms in the Gulf. December is presumably from the winter cold fronts. And then if we look in the ocean, the monthly means peak in October. There's a trend from March through June where the means decrease. So that's when we start getting that freshwater riverine input that has kind of peaked by June. And then we end up getting the heating of the seawater, and the solubility goes down. And if you look over at the standard deviation, June, July, so May, June, July are the peaks for standard deviation. All right, so then I looked at the fluxes. So I computed fluxes from 2 different ways. I coded in the various parameters needed for computing the flux. So converting the mole fraction to partial pressure by computing the pressure of the water vapor, etc. Computing the piston velocity and the solubility, and also using the MATLAB version of CO2 sys. So here is the air-sea CO2 flux time series. If I look at it in terms of means and standard deviations, if I use all the data, I get a net flux into the ocean of 9 millimole per cubic per square meter per day, with a standard deviation of 14.8. If I exclude the suspect data, I get a bigger flux into the ocean of minus 9.8, with a standard deviation of 13. So I can compute a climatology as well from that. So the top panel is a climatology. The black diamonds are the monthly mean air sea flux. So negative is into the ocean. From all the data, or blue is all the data. Black diamonds are the climatologies with the suspect data removed. So most months are pretty close together. It's June, there's a big discrepancy. The magenta inverted triangles are from the wave glider experiment, which I'm going to get to next. There's a red cross from a study by Lorenz and Kai. And then down below to the right, I've reproduced a figure from Huang et al. 2015. And these are results from combining data from multiple Gulf carbon cruises and coming up with air sea flux climatology. And they don't differ that much between the two, with the big exception of the October value in the Huang et al. Paper. So the results from the buoy up in the northern the northern part of the western Mississippi Bight are very similar to results in the rest of the central northern Gulf. So even though there's not a steady Mississippi River influence in that spot, there are some very similar results in terms of fluxes. Here is the standard deviation of the flux of the climatology. So there's a larger standard deviation in January and than other months, and it drops down to the August through October timeframe where the standard deviation is minimal. So the summary of the coastal Mississippi observations to date is that these observations are also in an area where seasonal hypoxia occurs. Despite the differences in nutrient loading between the Louisiana-Texas shelf and the western Mississippi Bight, the CO2 fluxes are comparable. And there, if you look at the time series, there are positive fluxes, so fluxes from the ocean to the atmosphere. The average is into the ocean, so it's a average sink of CO2. Also, on average, fluxes in the ocean are maximum from December through February, with a maximum in January. And fluxes into the ocean and the standard deviations are a minimum from July through October, when SST is high and generally winds are low, unless we have a tropical storm. And then finally, despite the increasing trend in atmospheric CO2 concentrations at this location, the sea surface shows a small to negative trend. Okay, so now on to the wave glider. So probably most of you are familiar with the wave glider, but I have some photos up above. So there's one taken from underwater, which shows the sled that has these movable slats, and as the waves go by, the slats propel the wave glider forward. And it's actually pulls pretty strongly if you've ever tried to recover one of these. So the instrumentation package on the wave glider, it was an Mbari wave glider. And you can see the set of instruments on it, which are similar to what's on the buoy. On the right is a GCAN product that was developed to show the glider location and its data. So it was kind of a live, when the glider was out there, it was a live, it was plotting live and people could click on it and see what it was measuring. So you can see the track starts at the Singus buoy, goes around the Mississippi River Delta, comes up to the Louisiana coast, and then it would go back to the buoy. So the two deployments, the wave glider on each one did a round trip. And the reason for the shape of the route is so that the glider would revisit GOMEC stations. So here is a picture. These are MODIS images from during the deployment when there were cloud-free images. So the first deployment was in October. It was deployed October 15th and recovered December 7th. The red dots on the magenta track are the GOMEC stations. And as you can see, the glider in both the October 19th and October 30th images, it doesn't look like chlorophyll values are very high out where the glider was operating. So here's a time series of the glider, and you'll notice that a lot of these values stop later in October, and that's because the wave glider was hit by a vessel and it destroyed the mast, and the mast had the air block, and I had the wind measurements. And so we only had the salinity, temperature, and dissolved oxygen at that point. But if you look at the top panel, it is latitude in blue and longitude in green. So as the glider moves down along the green line, it's moving to the west. As it's moving down along the blue line, it's moving to the south. So you can see it going southwest and then north, and back south again, and then back to the buoy. So so you can see for the short record we have of CO2 and wind that the water, at times the seawater mole fraction of CO2 was higher and sometimes lower than the atmospheric. So in this plot, green is the seawater, black is the atmospheric. And the fluxes varied. They were mostly negative, but they varied from positive to negative. Okay, so the second deployment, now we had some different conditions. So that deployment was from the 23rd of January 2013 to February of 2013, February 27th. And you can see that according to the MODIS image, the glider is going over from the buoy, it's passing through maybe a plume going to the northeast of the Mississippi River Delta. And then it goes around the delta and up to a region of high chlorophyll. So here are the time series again. Top panel is the same sort of thing with latitude and longitude, so you can see where the buoy, where the glider went. Now, if you look at any of the records here from the buoy, from the glider, wave glider going from the buoy around the delta, turning back around and coming back, the records are fairly symmetric until the glider just hung around the buoy until we picked it up. So the interesting thing here is that what we're seeing then is a relatively static field that the glider is sampling, so a relatively static heterogeneous field that the ocean that the glider is sampling through, and so we're getting a good view of how heterogeneous the area is spatially, and you can see the fluxes mostly are negative, and especially where the salinity is low, and the dissolved oxygen is high, just as you would expect. The salinity integral length scale from this is around 8 kilometers. So you can see, how salinity values are correlated. Here I've divided the fluxes into, I've bend them into 2 meter per second wind bends. So each of the data values is the mean of that in that bend, and then plus or minus a standard deviation. So the top panel is all of the data. The bottom panel is just when the wave glider got back to the buoy and just did a box pattern around it until we could pick it up. And so the top panel, it's mostly flux. The fluxes that we're looking at are fluxes that change mostly due to the temporal and the spatial variations. And then down below, it's mostly driven by time variations of the winds. So you can see a smaller standard deviation for that time period. Here are some of the property correlations. Again, where you have high DO, you have high pH, and vice versa. And you can also see that inverse relation between CO2 and pH. So to summarize for the wave glider, for deployment 1, where a lot of the measurements were cut short, the salinities that were measured were indicative of open shelf waters. And at this time of year, generally, they'd be vertically mixed. So there's higher salinity down below. If they're vertically mixed, then you have higher salinity in the surface. And there was a strong event in September, wind event, before we deployed. The CO2 flux averaged minus 0.83 millimoles per meter squared per day. So during that time period, it was a sink along the path while it was taking data. Then in the second deployment, as I mentioned, the similarities between the clockwise transect and the reverse counterclockwise illustrate the ability of a platform like this to measure the important spatial differences in a region like this, where you have lots of different river fronts. So you have primary fronts, you've got relic fronts, etc. Over the course of the second deployment, the fluxes varied from minus 55, almost minus 56, to plus 3.56 millimoles per square meter per day, with the average of minus 8.33. The fluxes during the period when the wave glider is going around the buoy were preferentially driven by variations in wind speed rather than other properties. All right, so now we'll look at the Singus buoy in coastal Louisiana. So there was a understandable desire to try to get some measurements in the notorious dead zone. So Dwight Gledhill at the OAP office had someone at NOAA look at at a kind of a chlorophyll climatology and found a hotspot that would be a good place to deploy the buoy, to move it to. So we moved it in July 2017. So the top shows that map that I showed before, where the buoy location is. Down below, I've expanded it out so you can see where the Singus buoy is and where the WAVESYS station is. It's about a half a kilometer apart. All those white lines are pipelines. And so I had to pick a place where I wouldn't drop a heavy anchor onto a pipeline and make the news. So that was the place I chose. And then on the PMEL website, it's known as PMEL Coastal Louisiana. When we first put it out, they did not have a pH sensor for us to put on it. So we don't have a pH record. You can see the mole fraction of CO2 mostly negative relative to the air and sometimes being positive. We lost temperature and salinity, and the gap you see there is we went out to the buoy to find out what was going on, and we couldn't get a signal to the CTD. It turned out the CTD was missing, and it drained the battery. So the gap there is when after the battery drained, we made several attempts to go out and replace parts. We had to use divers, and weather and boat schedules prevented us from doing it right away. But so the second part there is when we replaced the equilibrator, the battery, and the CTD system. So you can see everything was working well. There's a black dashed line, and that's when the Bonnet-Carré spillway opened this year. So it opened on March 8th, I believe. And so what that means is that the Mississippi River is at coming out of New Orleans at 1.25 million cubic feet per second. And so the river was flooding before that, so you can see the chlorophyll increasing, the pH increasing, salinity dropping, temperature dropping, dissolved oxygen going up, and the turbidity also increasing. Here's a picture of the Bonnet-Carré spillway, and so far what the opening pace has been. So recently they've started closing down some of the bays, but they think that it's gonna be open. They think that after they close it, it's gonna have to open again this year, which would be unprecedented. So here I've just focused in on the time period after we replaced the temperature, the CTD and other ancillary sensors. So you can see better the record from these instruments. So the summary for the coastal Louisiana station is that the first year of deployment will end this July. So then we'll have a nearly full year of data that we can start looking at seasonal cycles, things like that. This first year, it seems like every year is anomalous, but this year is likely to be more anomalous because, as I mentioned, there's the flooding on the Mississippi, and we're expecting another flooding pulse to come down later in the spring. There was a low variance in seawater mole fraction of CO2 in January to mid-March. I forgot to point that out in the earlier parts of the presentation, but that's a common feature where there's a low invariance at that time of year. And finally, one of the things we're all working at is pursuing opportunities to couple seafloor monitoring of hypoxia and OA parameters at or near the buoy site. So we're looking for opportunities to put pH and CO2 sensors, maybe DIC sensors down at the on the seafloor, maybe on either at a bottom package acoustically talking to the buoy, or on the LSU site that's nearby. Okay, so finally, the ability to autonomously monitor CO2 and other carbonate system parameters gives you information over a wide range of time scales. So for example, there's a diurnal cycle of about 6%. So that's going to affect, if you're out on a ship and you're doing some stations in the day and you're doing some stations at night, that's going to introduce some aliasing effects. So you can look at the full scale from, the sampling frequency, in this case is once every 3 hours, to however long your mooring is out. So that's the beauty of these moorings. And then also autonomous moving platforms like the Wave Glider or others can give you information on the spatial variability in these very heterogeneous systems where there's lots of different river inputs, and on very small scales that you can't easily see in remote sensing data. And finally, my final point is the Northern Gulf has a widespread region of seasonal hypoxia east and west of the Mississippi River Delta. And autonomous OA seafloor platforms beneath OA moorings could give us the ability to study both the development of ocean acidification at the surface, but also hypoxia and ocean acidification driven by the seasonal effects. So that's it. Thank you.
Thank you so much, Stephen. That was really interesting. Does anybody have any questions? Feel free to add into the chat box. Or if you'd like to unmute yourself to ask a question, I'm sure it may be a little complex. Feel free to do so. Oh, I think we have one question. Okay, I have a question. Are there more recent nutrient data showing MS bite low nutrient compared to Mars outflow?
Yes, there is. There are data from a number of sources. So one is the for the cruises I talked about for the GoMarie Consortium, the Concord Consortium. There's nutrient data from those cruises. The Lake Pontchartrain Basin Foundation does sampling, I think on a monthly basis, in the western side of that western Mississippi Bight, and they have nutrient data. Yeah, so there are other data sources for that. And it's interesting, in last year in 2016, when the Bonnie Carey spillway was opened in January, was the earliest time it had ever opened, so it was January 10th, I believe. The nutrient levels measured in the western Mississippi Sound associated with the spillway water coming out were very close to Mississippi River values. So, and that probably was because of the time of year, because it was very cold and there wasn't a lot of productivity, and so not a lot of uptake. Usually we see more of a drawdown while the water's coming through Lake Pontchartrain to get to Mississippi River.
Great.
And there are people out monitoring for this opening as well, but east of the Delta.
Great. That question was from Katie. Thanks, Katie. And we have another question from Dash. On the buoy, what depth are the sensors in?
Okay, the sensors, so it depends on the sensor. So the CO2 system, the float, so the equilibrator has a styrofoam float, and then there is a copper pipe that extends about, if I remember right, it's about 4 centimeters below maybe 10 centimeters below the float. So that was probably about 15 centimeters below the water line of the float, but I could find out more exact numbers if he's interested in that. Um, the CTD with the dissolved oxygen and fluorometers and the pH sensor are about 1/2 meter below the sea surface.
Okay. And Dash, you can email me if you are interested in getting some more information on that. And then Jinping, it has a question. It's
Okay.
what's the mechanism for decreasing seawater CO2 over time?
Well, that's a good question. Um, uh, so I'm a physical oceanographer, so take my answer with a grain of salt, but maybe there's an increase in primary production over time. So it'd be like an increased biological pump.
Like bioactivity. Okay, anybody else? The question? I think we made pretty good timing. It's 1
Good.
minute to, yeah, it's one, oh, here we go. I think Katie has one more.
Okay.
Has anyone taken surface and bottom water samples at new buoy location?
Yes, we don't have that back yet. And we should be taking another sample soon because we have another, we try to go quarterly to take water samples there.
Okay. Yeah, I think that's it.
All right.
It is now 2 p.m. Eastern, 1 p.m. Central, and I think that's a wrap. Stephen, that was awesome. Thank you so much.
Thank
And
you.
if anyone has additional questions, feel free to email me or Stephen. I left my email in the thread, the chat thread, and we can get you some more information if you're interested. So I'd just like to thank everybody for participating, and a big thank you for Stephen for taking the time to do this. We really appreciate it.
Bye-bye.
Bye, Stephen. Thank you, everybody.